Ooh. Yeah. Yeah, thanks, and welcome to day 2. I'm going to be talking about generative AI and also applied NLP. So basically, getting stuff done, doing real things. And some of you might know me from my work on spaCy. spaCy is an open source library for natural language processing in Python. And it was really designed from day 1 to be used in real products. And that also means we had to do a lot of this boring stuff like backwards compatibility, making sure we're not breaking people's code, which actually had a really fun, nice side effect. And that is ChatGPT and similar models are actually really good at writing spaCy code, so at least for now. So if you haven't checked it out, definitely try it. You can have it even write your rules to solve your NLP problems. And we also developed Prodigy, which is a modern annotation tool for creating training data and evaluation data for machine learning models, semi-automating your data creation, data development workflows. And it's entirely scriptable in Python. And also a lot of these ideas that I'll be talking about today can be used in Prodigy. And finally, we also recently announced that as a company, we're going back to running as a more independent-minded, self-sufficient company and going back to our roots, essentially. And that really lets us focus on our core stack and also the tools and workflows we think are currently missing from the ecosystem, including, again, some ideas that I'll be mentioning in this talk. Large language models, generative models, large generative models have really caught on, and there are definitely a lot of reasons why they're so popular and people like to use them. And one of them is, well, because the models are so big, you're getting really good contextual results using basically no examples and no training data. So that's very cool. And they're also easy to use and to configure. So you start off with a prompt, and you immediately get a result. And that also makes them really good for prototyping. So previously, you needed at least some number of examples and some work, 40 hours of work, going into a model before you had at least something that was, even if it was kind of shit. So now you can skip that part, and that's all great. But there are also challenges to a lot of the workflows in industry. And one of them is, well, we actually don't really know what's going on under the hood with a lot of models. If they're behind an API, we know even less. Even if a model is open source, you're doing a lot of things at once. So it can be quite difficult to really understand and explain why your model is making a specific decision. And because the models are so large, we also have problems with efficiency. They are slow. If you can host them yourself, but that's very difficult to scale. You might have to use an API, but then you're kind of at the mercy of an API provider, so that can be very tricky. And that also leads into the question of data privacy. For a lot of use cases, the data needs to stay entirely on in-house servers, can't even go anywhere on the internet. And so if you're using an API, that's kind of not possible, so you need to host it yourself, which leads you to efficiency and scaling problems. So these are all things that really, as an industry, as a community, people are working on. And in this talk, I'll also show you some solutions and some ideas for how you can still use the latest models without running into these problems and challenges. And so how did we get here? One reason I would say why we're all here today is fundamentally what we're trying to do is we're trying to tell computers what to do. That's kind of the core of everything. And in the beginning, well, the way you would normally do that is you have rules or instructions, conditional logic, regular expressions. And then with machine learning, we got a new way to tell computers what to do. That's programming by example, so also referred to as supervised learning. So you can show the machine examples of what you want and hope that it can generalize based on that. And now, with in-context learning, we unlocked basically a new way to tell computers what to do again, and that is also through rules and instructions in the form of natural language prompts. And there are kind of pros and cons here. Instructions are nice because they're really inherently human-shaped, and they map how you tell a human what to do. And that also makes them pretty easy to get started with, even for non-experts. But on the other hand, there's a risk of data drift if your data, or in the case of prompt engineering, your model changes, your rules might not apply anymore. On the other hand, examples, they let you really express more nuanced and intuitive behaviors, like stuff where you kind of know what the answer is, but you can't fully express it in an instruction. And they also let you provide examples that are really specific to your use case and what you're working on. But they can also be very labor-intensive to create. They need to be consistent, so you need to spend time on that and really focus on the data quality. So the question is, what's next? How can we maybe combine the best of both worlds and find a way to tell computers what to do in the most efficient and best possible way? And if you have a large language model or large generative model and you wanted to do something really specific or create really specific structured output for your specific task, the way you usually do it is you start off with a prompt template, you have your text that goes in, often you have a corresponding parser that takes the human-readable output and transforms that into the structure you're interested in, and then you get your task-specific output. And that's actually also something we developed for our extension library, spaCy LLM. If you haven't seen that yet, it basically adds some abstractions over different models and takes care of the prompting and transforming the output to structured data. So you have kind of the same experience, whether you're using a large language model, a model you've trained yourself, or just some rules and basic logic. And now, of course, what you can do is, hey, you have a system here, you have a prototype here, you can ship that. But another thing you can also do is you can work on replacing those components, and you can work on replacing them with distilled specific components that really only do what you're interested in. And the advantage of that is that you really have a modular system. And if we've learned one thing from general software engineering, it's that modularity is very good, because it means you can work on every component individually, and you can plug things together in different ways. You also end up with components that are really small and fast. I'll show you some examples of that later in the talk. These are components, because they're small and fast, you can run them in-house, you can run them yourself. Sometimes you don't even really need fancy GPUs for them, so it allows you to really keep your data fully private and under your control. So that's pretty cool. And of course, if you're doing this, you don't just want to match the performance that you have from the large language model. You ideally want to make it even better, because you're working on this and you can. So the way you do this is, well, ideally, you need a human in the loop. And here's a little example of a possible workflow. So you start out with a large model that has a lot of weights, can do a lot of things, and of course, first, you want to evaluate it. Without an evaluation, you have absolutely no idea whether anything you're doing is making a difference, if it's making it better, if it's making it worse. This is something that's often glossed over, but I think it's actually a really crucial step in any workflow. And that gives you a baseline, so you know what you're up against, and you can now prompt your model using all the weights that it has available and pipe that forward into an interface. For example, this is an example of our tool Prodigy, and you can have a human look at it and make corrections to things that the model is getting wrong, and save the output that's really only the output that's relevant to your specific task. And using transfer learning, that allows you to train a component that's much more specific and only deals with the subset of what you're interested in. And just because there's a lot of talk about in-context learning at the moment, and that's what a lot of the research is focused on, it doesn't mean that transfer learning is somehow outdated or has been replaced. It's simply a different technique that we can use, and it especially comes in very handy here if we're looking at a scalable way to use specific examples. And what we're doing here is basically we continue this until our distilled model beats and ideally also exceeds the baseline. And to give you an example of this in practice, I brought you a little case study that we did recently with S&P Global. And what they're doing is they're working on real-time commodities trading. So if crude oil is traded somewhere, they want to extract the structured attributes and publish that as a data feed for their customers. And of course, this is information that can really significantly move markets if you have access to it. So it's a very high security environment. Nothing can leave their servers. I actually went to visit them recently, and the analysts really sit in like this glass box that you can only access if you have the key card. So it's all very controlled, even internally, and that means the pipelines have to run in-house. And what they did is they used a large language model that they have had access to during annotation, so during development time, and used it to create better data faster. And with some clever tricks that also are shared in the blog post, if you're interested in this particular case study, they were able to speed up their data development process by 10 times, do it 10 times faster with a human and automation by a model in the loop. And they currently have 8 pipelines in production, probably more at this point. And if you're looking at the results, you can see we're getting really high accuracies here and have a model that's 6 megabytes. Like it's not gigabytes, it's megabytes running at 16,000 words per second. And if you're looking at the results table, you can not only see the accuracy scores, but you can also see how long it took. So the data development time, that's the time it would have taken like one individual person to do it all on their own. And so with 2 people, that's like a bit under a work day and of work to build one of these components. So if you think about like other stuff you spend time on in your day-to-day work, you've probably spent more time trying to get CUDA installed or getting your GPU to run in the first place than this. So this is like all extremely promising and very exciting. So how did they do this? Like, what's the secret? What did they do differently? And one answer to that is refactoring. Refactoring is something you're probably familiar with from your day-to-day work. You do it with code all the time, but it also applies to your data and to the structure and schema that you want to use in your application. And I would actually say from our experience, this is really the part that most teams struggle with, because there is no one-size-fits-all answer. And it really depends. It's incredibly specific to what you're doing, and it's a process. And it's a process that's pretty tricky. Because in traditional software development, we have code, we usually have a compiler, and at the end of it, you get a program out of it. Now, in Software 2.0, you have data, and you have an algorithm and a model that comes out of it. And if you're not happy with the program you've built here, of course, you can go and tweak the compiler. But you probably wouldn't do that. You'd probably go and edit your code. And the same is true for Software 2.0 and working with data. And if you want to see, hey, is my program good? Is it doing what I want? Well, you write tests. And in the case of a model, you have an evaluation. Again, a lot of people don't like doing that or skip that part, which you can. I mean, just like you can skip writing tests and not write any tests at all. But of course, that also gives you no way of knowing whether any changes you make break things. And we've accepted that as a best practice. And the same is true for evaluating your models. So again, this is where you ideally want to refactor. You can tweak hyperparameters, but usually you really want to look at your data and change your data in order to get a better model and iterate on that solution until you have something that you're happy with. And again, this part is hard, but there are some tips and some concepts that can basically help you with this. And now you might think, well, do I really need to do all of that? Like, what I'm trying to do here is really just something simple. Do I really need to spend so much time and think about my schemas and try out different ideas? Aren't there just things where there's a clear answer? And of course there are, but I've brought you some examples to show you that even things that might seem simple at first actually do require some reasoning and refactoring. So one of my favorite examples examples is this. We have 2 sentences, I love cats, I hate cats. And now the question is, are these 2 sentences similar or not? Maybe we could do a show of hands, like who thinks that those 2 should be considered similar? Yeah, OK. And who thinks they're not similar? Yeah, so we get about a 50-50 split, which is actually usually how it goes. And as you might have guessed, this is a trick question because, of course, it depends. Out of all the things you could say in the English language, yes, of course, these 2 sentences are incredibly similar. It's sentiment about cats. But if you're building a dating app and you're trying to match people up based on their profiles, well, you probably want to consider these 2 things as very dissimilar. And so, again, your application context always matters. And the same is true for more complex, structured extraction and information extraction questions. So this example was inspired by a workshop we did at PyData New York last year, which actually in turn was inspired by a workshop we did at this very conference last year, Vincent and I. And what we were doing is we, together with a group, streamed in texts about cooking and from recipes from the cooking subreddit, and we try to extract ingredients, dishes, and equipment. And at the workshop in New York, we actually managed to beat the few-shot GPT baseline with a model that ended up being 20 times faster, and was the task-specific component really for this specific thing that we're trying to extract. And you might think, well, it's pretty straightforward, pretty simple. If we define, so for those unfamiliar, Cheetos, it's a type of crisp that has, I would say, a very dedicated fan following. And if you define dish as something that's a ready-made product that you eat, Cheetos is probably a dish. But then as soon as we started looking at the data, which is also nice in the workshop, you have time to really discuss a lot of things with the group, we came across more examples. And it turns out that especially Americans really like using stuff like crisps as an ingredient, essentially, in a dish. So we need to distinguish here between Cheetos as an ingredient and Cheetos as its own dish, and decide on a consistent policy. And the same is true for equipment. Rolling pin, that's pretty straightforward, but then the question is, what do we do with a bowl? What about a small bowl? What about a small microwave-safe bowl, small, lightly warmed bowl? We have all of these different descriptors of that bowl. Should we include them? Should we not include them? And if we take a step back, we see that not only do we have logic here that's really specific to our application and to what we're trying to build, the fact that we are looking for equipment for cooking, there are also a lot of features that are really inherent to the language itself and to how we even express the fact that that bowl is small, and that's the general purpose, completely business-independent logic, and that's in this case the grammar. So you can also really think of it as factoring out your business logic, and we can break that down into a formula like this. So as a little pseudocode example, that's kind of how it would work, and that's kind of how the task works. And what we have here is stuff that's not specific to your business logic. We have things like words, grammar, syntax, and also information that's directly present in the text. And on the other side of your business logic, what we have is stuff like external knowledge, things that are not present in the text, and also facts that can change over time. So if you're unsure how to approach this, one thing that really helps is taking a step back and trying to think about it from the model's point of view. If you're the model, you're trying to solve a specific task, what information do you have available in the text and in the language itself, and what are things that you can basically factor out? Just the same way you factor out reusable logic when you're refactoring software and refactoring code, you can refactor your data in this way and the logic you use to extract structured information from it. So also, to give you another example of a project that actually did this, this is another case study we did quite recently with GitLab that you're probably familiar with. And what they want to do is they want to extract actionable insights from support tickets and usage questions that they get. And as you can imagine, there's a lot of content online. They want to improve their documentation. They want to help their support engineers, better support the community. And for that, they analyzed 1 year of support tickets. And you might think, oh, support tickets, like that's not specifically sensitive. But if you think about it, even just a log message or path can potentially include a lot of user information. So it's also a high security environment, needs to run entirely offline. And what's also important is the solution they were looking to build needs to be easy to adapt to new scenarios and business questions. For example, things like, are people adopting the newer version? What do people think about the latest features? Or how many people are still using an older version of the self-hosted platform? And there's a lot in there that changes over time, like the fact that which version is old. That's something that's not inherent in the text. And so as a first step, what they did is they separated the general purpose features from the product-specific logic. And here's one example of some, it's pretty simple, but actually makes a big difference. You have a general purpose URL, but then you also can add a label on top of that, which is specific to their documentation or their version, because these are things that can change over time, whether a version is old or not. So this is, you could also read more in the case study, see some examples, but they basically managed to build a system that was incredibly fast, runs internally, and can easily be extended with any question they might have about how users are using their platform and what best to do. And if we're looking at that, it's actually there's actually a very, very important difference here between use cases where you know what you want and use cases where you don't. If we're looking at, if they were instead doing some data exploration, they had all their support tickets and not really an idea of, OK, what are we trying to do with it? That's where retrieval augmented generation, or RAG, comes in really, really handy, because you can embed all of your tickets, and you can look at similarities, and you can basically ask any questions about your data, and in that way, explore what's in it. But if you are in the situation where you actually know quite specifically, here's the schema that I want, which is often the case for applied NLP. Very rarely you come in and have no idea what you want to be doing. You often have a very clear picture of here's what I want. You're basically paying the cost of a technology like RAG, which is where the big advantage is the flexibility, without actually using any of the benefits. So an alternative approach is, well, you can also refactor it and do your information extraction upfront, and introduce constraints, which is also something that's actually very important and not necessarily a bad thing. If you have constraints, introduce them. You do it the same way in your software, and you can do it the same way in your data. And another nice advantage here that you get is that you basically end up with a solution that's completely interface agnostic, because ultimately, language and dialogue interfaces and chat interfaces, they're really just that. They are a different interface. And whether it's the right interface for what you're trying to do is a whole other question. And But if we're looking at solutions people are building, especially now with all the excitement around chatbots again, I don't know if any of you remember the first chatbot hype in 2015 maybe, so about 10 years ago. For those who don't and weren't around yet, it was basically kind of like it is now, just with fewer people and significantly worse tech. But people really imagined workflows of the future as talking to some kind of robot. And not all of this worked out. And I think one thing, if we're trying to imagine the technology of the future, one thing that I think really helps and that I really like to do is looking at the past and looking how we solved and automated things in the past and what worked and what didn't. And one of my all-time favorite examples that you might have seen before is this peculiar job. So starting with the Industrial Revolution and up until the 1950s, people would hire so-called knocker-uppers to walk around the neighborhood with a stick and knock on people's windows. And that was before alarm clocks were affordable for people, before alarm clocks were reliable enough. So if you had to get up for work, you hire a knocker-upper, and they would come and knock on your window. So of course, this is a profession that has long died out, and we have replaced this job successfully with technology. But what we did was we built alarm clocks. We didn't build a window knocking machine. So that leads me to something that I also like to call the window knocking machine test. And it basically means whenever you're tasked with automating something that was previously performed by a human, ask yourself, are you building a window knocking machine, or are you actually designing an alarm clock? And to give you an example of this, here's a very classic conversation people might have with a chatbot, especially scheduling appointments is a huge pain. And so people have always been trying to automate this. And you see scheduling conflicts here, you have time zones. And this is something that is actually quite doable now with the technology we have. But the question is it actually the best solution? And an alternative approach was introduced by a product called Calendly, which I love. If you haven't checked it out, I highly recommend using it. You sync it with your calendar. You send someone else a link. They can sync it with their calendar. They can book an appointment. And so in seconds, you have solved the otherwise really painful problem of scheduling an appointment. And it doesn't even really need AI at its core. It's simply a different way and a different reimagined solution for the same problem. So you could also say this chatbot here is really the window knocking machine in this example, whereas Calendly solves it with an alarm clock. Ooh. And not all examples are this clear-cut and black and white. We also, with technologies like retrieval augmented generation, we really have the opportunity to chat with our data. And that can be pretty useful, and it can replace a lot of other interfaces and other ways of engaging with the data and get us the answers faster. And here, it really depends what works best for your specific scenario. But what I can already say is one big misconception people often have about professional tooling is this idea that in order to make things simple and easy, we have to add more layers of abstraction. And that's how we end up with these one line of code, one-click tools that sound really nice in theory, but have users immediately hit a wall as soon as they're trying to do something that maybe wasn't intended by the developer. And so if your problem is that your existing interface is bad and people don't like using it and it's inefficient, it's usually much better to go and fix that instead of adding even more layers of abstraction and adding another interface on top, which is a conversational interface. So ultimately, you still need to make product decisions and think about the users who are going to be interacting with your system and how you can best support them, and think beyond just a conversational interface being the solution. It's an interface, nothing more. So to sum up what I've been talking about today and my thoughts for how we should approach applied NLP and getting stuff done with all the new opportunities we have available with generative AI, I think it's really important to always take a step back and reason and refactor your solutions. It's still true that everything that matters is in your data. And just like it is with code, where the first idea you have is usually not the best one and the one you end up shipping to production, the same is true for data and the structure of data. And so you also want to keep an open mind and let the data surprise you. And as soon as you engage with the data, you often get new ideas and new edge cases that you weren't aware of before. And that little exercise we did with Cheetos, I also highly recommend doing that. If you're working in a company with different stakeholders and you're kind of trying to get that point across that, like, hey, we actually have to engage with our problems. AI isn't, there's not a magical AI fix. We need to first decide what we want and come up with a consistent plan. Do a little exercise, invite all your stakeholders, and then you can have hours-long discussions about whether the forehead is part of your face or whether Cheetos is a dish. And it's usually very effective in driving home that point to everyone. And next, conversational AI, conversational interfaces are really just interfaces. And you want to think beyond just chatbots and dialogue. Whatever you're building, you don't want to build the window knocking machine. You want to be building the alarm clock. And that might require solving the same problem, but in a very different way, and not automating exactly what the workflow is with a human in the process. And finally, stay ambitious. There's really no need to compromise on a lot of the software development best practices that we have built up as an industry over the years. Just because there are new technologies and tools available doesn't mean that we have to go, oh, new paradigm, baby, and throw everything out of the window that was working before. There are a lot of best practices like modularity and transparency that really make sense and that you can also apply even with new workflows. And there's absolutely no need to compromise on data privacy or efficiency. Like, as we've seen in some of the examples, it's totally possible to build these systems and use the latest technologies to your advantage by taking a step back, reasoning, and being smart about it. Thank you.
Are there any questions in the room for Ines? I see the first hand raised here.
Thanks. Hi. Thanks, Ines. That was great. This is actually kind of a noob question, but I feel like it's worth asking maybe. How do you conceive of the difference between model in the loop and human in the loop? Like, how do you think of the difference? And is there like a technical point where you'd be like, it's one or the other? Is it the amount of time spent in one system or the other? Because I hear these languages being used a lot, and it's actually like maybe nice to disambiguate what we mean when we say one or the other.
Oh, it's like what we mean by having a human in the loop
versus having the model in the loop.
Yeah, I mean, it is arguably a bit vague. So usually, when I'm talking about having a human in the loop in the development process, often that refers to making corrections, reviewing what the model is doing, and creating, basically having the human have the final say over the data. Whereas model in the loop, again, actually, yes, that's also used for all kinds of things. I'm basically mostly using it to describe automation, where you actually have a model. You have a model to create the structure and semi-automate the annotation process. And often, actually, that's combined with the human in the loop. You have the model, you have the human looking at things and creating data this way. And of course, there's also having that concept of having the model in the loop that's updated as you create data, for example. That's possible, but actually, I think with transfer learning, that can also be part of it. Like, you train a component that you then use to semi-automate your annotation. You have the human review it and kind of have the workflow like this. But it's true that people use these terms to mean all kinds of things, but that's how I use them.
Any more questions? I see a couple of hands raised here. Let me start here.
Thank you very much for your talk. A question I would have with regards to the sort of the business cases that you did. And so my experience is also often that if you do say the refactoring, then you find that actually the taxonomy that you were using, or what you were trying to extract, that it's insufficient, or that you want to extract other features. What is your experience in that case of, okay, how do you then adopt the taxonomy that you want to create in this process?
Yeah, so what you describe is definitely true. Like, we see this all the time. Like, it's, as I think developers, we like to divide the world neatly into categories, and that just doesn't work like that. So as soon as you start, you realize, oh, I want to split this up differently. And I think that's, you kind of have this, end up with this chicken and egg problem where, you have your idea, you design the label scheme, and then, as you keep going, that changes, and then that changes the product again. And I think the best and only effective solution is iterating and having workflows that support that sort of iteration, and also doing things in-house and having it embedded in your team. Like, if you say collecting annotations or collecting data and you outsource that, and it needs a whole like meeting and approval and so on, like, that's of course inefficient, and I think that also leads people to building systems that are worse. But if you kind of embed that whole process into the development process, and as a developer try things out, see how you go, and can kind of iterate on that faster, I think that's that's very important, and that comes down to having good tooling. But I think definitely people shouldn't be afraid to change their taxonomies or change their schemas to match the actual reality. And also, doing this idea of factoring out the business logic, looking at, okay, what can I generalize? How can I make the problem easier for the model? Because, again, I think Vincent also said that in his talk yesterday, you are allowed to make your problems easier. You don't, this is not a competition. This is also not academia. Like, you're allowed to make a problem easier.
Thank you very much.
More questions?
Thank you. Fun fact, my first pet project was trying to get ingredients using spaCy, but I stopped when I didn't know how to deal with the small balls, etc. So maybe I have to pick it up again. Yeah. But my question is, if you have a task where, for example, a certain sub-part is very critical to get right, and if you get it wrong, you must be able to able to explain why it is wrong. But not everything is that critical. How would you go about these critical questions? I can imagine that S&P also has that, for example.
I think so. S&P, as an example, what they did was they also looked at, okay, which cases can we solve deterministically? Because there are some where they know, okay, it can really only be this, so it can be a subset of this, and handle those separately. And I think also a modular approach is great here, because if you have, let's say you have one category that other things depend on, you don't want to have a workflow where you have this one monolithic model that needs to get everything right together, and if it doesn't, you kind of have no idea why. And I think they are breaking things down into components and having, say, one component that really only deals with the critical part, and that you can, debug and really work on independently, and where you can, also maybe for that specific thing choose a methodology that's a lot more explainable than having a big model try to do 5 things at once, or looking at the characteristics, like what is already in the grammar, for example, that you can take advantage of. I mean, obviously it depends on your use case, but I think for these kinds of things, having a modular workflow is really important, and it's the same you would do for writing code, just that we're working with data here.
All right, thank you.
Any more questions?
Yeah, you were talking about transfer learning to make a model task specific, and that sounds nice, but how does it work? Like, how does transfer learning make the model smaller and faster?
Yeah, that's a good question. So, I mean, inherently, if you're training a task-specific model, you usually start off with some embeddings to give you more context about the individual words, and then you train a task-specific layer on top, and that layer can usually be a lot simpler because it only needs to do, say, one specific thing, or predict the category, or predict character offsets. And the nice thing about transfer learning is that it really lets you start off with a lot of knowledge about the language and the world, and use that to your advantage to solve, in your very small task-specific network. So depending on, of course, how small and fast always depends. Like, often in a lot of these cases, you're looking at something the size of bird. That's usually pretty good. And then, you really only have the overhead from the embeddings. And yeah, and the 6 megabyte example, that was also, that is pretty extreme. That uses CNN-based models. And that really, depends on whether that works for your use case. But even, a few hundred megabytes, up to a gigabyte is still relatively small if you compare it to a massive model, and that's because you take advantage of the embeddings and you train a task-specific layer that only needs to do one thing.
Okay, thank you.
I think we have time for maybe one more question.
This one.
Hi, so I was thinking about like non-discriminative and unstructured tasks, like say summarization.
Yep.
I wondered what refactoring in the feedback process looks like in that kind of task, where you don't have a schema and you're relying more on your guidelines and the relationship with the annotation process.
Yeah, I mean that's a good question. So I mean it depends on what you're trying to do. Like if you even for tasks where you have where the output is human readable, there are still things you can potentially factor out. And even nowadays, like people talk about RAG and people talk about agents, but if you take a step back, a lot of a routing agent that decides which model to use is really just a text classifier. And if you look at it that way, for example, there might be ways in which you can make the summarization easier by first looking at, okay, is this text of this specific type? If so, I'll use that model. If not, I will maybe do something else to it. Or you might have a workflow where you first extract the key points and then pass only those to an LLM, which is also a workflow actually that I think GitLab is working on. And I'm excited to follow along because they also first extracted the structured data and are then passing that to a very small local LLM that only takes care of getting that input and formulating a sentence out of it. So you don't have the model that needs to do everything. So the structured data is the source of truth, and that also really changes the calculation for runtime. So they are definitely things like that you can do, but it is also something. It really depends, and you need to engage with the problem. But I think there are a lot of opportunities also for use cases where the output is text.
All right, thank you so much, Ines,
also, I have
for your
stickers,
amazing talk.
including new stickers. So meet me for stickers.
They're really beautiful stickers, so I definitely suggest you go check them out.